index of dispersion from our data. Now what we have are the four distances here. Remember, for Eberhardt's I sub e over here, what we need is the standard deviation, we need the mean, and we need to square that value, and then we need to add 1. And that's all there is to that. So let's go ahead and get started. The first thing we need to do is find out the minimum distance from each random point, and we're going to do that by calculating equals min. Okay, some of you may have already figured this out, but this middle min will do that, and that's very easy, so we'll just drag that down through all of our data. This is really fast. Those are all the minimum values, so those are the distances. The next thing we're going to want is we're going to want a standard deviation, and we're going to want an average. All right, so this is going to be equal to STDEV of what? This entire column here. Those are all the nearest distances. Come on, baby, drag down. It's really not going so well. It wasn't supposed to go that far down. Let's just go that far. Okay. And then return, and that gives us the standard deviation, and the average then, of course, is going to be equal to the average of the same set of numbers, which is going to range from here. I'm going to do this the easier way now. Click there, then I'm just going to go to the end and shift click down there, and close parentheses, and we're done. So that is the average. So those two numbers we have, and what we're going to do is square the ratio of those. So this is going to be S over X bar here, and this is going to equal the standard deviation divided by X bar, which is that number. And we're going to go ahead and square this whole thing. So I'll just put parentheses around it, and we'll raise it to the power of 2. And there it is, and then we're going to add 1. So we should annotate this so that it says SX bar, and we raise it to the power of 2, up 2, like that. And then for the cell below it, this is just going to be the +1 cell. So the +1 cell, well, I'll write it out, +1 is going to equal whatever this cell is, +1. Now, okay, now that number, 1.12. Now this number is going to be evaluated using the chi-square. We know from our, let's see if we can take a look over here quickly at our chi-square table. We know from reading our lab report here that Eberhardt's test is performed like this, and we also know that in the event of we have a similar number, 1.14, we're going to evaluate that on the chi-square with the number of observations being the n value there, the size. So I'm going to go down here. We got 41 is our line number, but we're 2 down, so we're 39. So n equals 39 in case anybody's wondering. And then the chi-square, let's call it the p-value here. Let's go take a look again at that chart, and that chart will then tell us that between these two numbers is where we are. This is 0.05 and 0.05 on the two tails. Everything in the middle is random distribution, 1.27 being right in the middle. And we're going to be at 39, which puts us just about 40. So I'm going to evaluate it at 40 down here. And we have to be outside of 1.2 and 1.34 to be anything but random. We compare our number 1.12. You'll see on the table that we're at the left-hand side down here, which is less than 0.005 probability of getting a value as small as 1.17, I believe it says on here. So ours is even smaller than that. So we're less than 0.005. Had we used 0.05 on each tail, we would have rejected the null of Poisson, and we do reject the null of Poisson in this data. As well, we could use the 0.025 on each tail, which would be the standard 95% confidence interval, which would also reject the Poisson. So our data is not random, it is uniform. Here in the Excel data sheet, what you want to do is write in that our p-value is less than 0.005, and our result here is going to be Poisson rejected, and we're going to support uniform distribution.